hard it is.
Yeah.
All right.
Yeah.
It's definitely.
So notes, probably some stuff right now. Let's back up here a little bit because what I realize is we need a little bit of work here on just plain old derivatives because without the knowledge of derivatives, you know obviously antiderivatives are hard because they're based on that, based on the derivatives. So we've got to really make sure we can understand that. The gateway test is next week. Probably Tuesday would be the earliest it would be. Okay. So right now I'm debating between Tuesday and Wednesday. So those are the. Yeah. I have a feeling I know what your vote would be. So we'll kind of see. That's just like the gateway test was for derivatives. 10 questions. Have to get 8 right. Keep taking it until you pass it. You got, so many tries, the grade goes down the more you try and all that. Everything's the same as it was for derivatives. Okay, so let's back up here and just kind of review here where we've come from, where we're at, notation-wise, all that stuff. So we started all of this in Chapter 5 with the definite integral, okay, which is the integral from a to b, some function. What that means is the area between that function and the x-axis. Okay, it's a number. A definite integral is a number answer. It's a fixed piece of area that has a value. So we can evaluate a definite integral. Okay, evaluate means find the value. Okay, now we have 3 different ways we can do that. Okay, one way is if the area is a geometric shape, we can just calculate it geometrically, but that doesn't happen very often. Right? You don't get many functions that create geometric shapes. So that's a very limited way of doing it. You've got approximation. We could count squares, or we could kind of estimate what the area is. Okay? Now, and that's not a great option because it's not exact. It's an approximation. Now, it turns out that there may be some times that that's the best we can do. And that's what we have to do. And actually, later here in Chapter 5, we're going to work on approximation techniques. Okay, ways of approximating. Okay, so we'll get into that more. For right now, that just means we'll kind of estimate the areas, all that is. So the big one for us right now is the last one, Fundamental Theorem Part 2. Now, that's great because it'll do exact areas of non-geometric shapes. So that's great. The downside to the last one is what? You have to be able to find the antiderivative of the function. And it turns out there are some functions that do not have an antiderivative. Matter of fact, some of them are not even that complicated looking. This function right here, sine of x squared. If we were wanting to find the area from, 0 to 1 of sine of x squared, if we wanted to do this, we could not use the Fundamental Theorem Part 2 because there is no antiderivative of that function. There just isn't. Because there's no function that when you do the derivative of it will give you sine of x squared. So it doesn't have an antiderivative. So we can't use Fundamental Theorem Part 2, and it's not a geometric shape. So the only option we have is an approximation technique. So we will be studying that later. Okay. So for right now, we're going to focus on functions that do have antiderivatives. And how do we find them? So we can use Fundamental Theorem Part 2. That's what we're doing. Okay. So let's investigate the 3 types of integrals we've had so far. Because you've noticed that in our problems, we've been doing integrals that don't have anything on it. They're just integrals without an a and a b, right? And I just told you, hey, that just means antiderivative, and I just told you that. Well, now let's step back and let's talk about why that is. Okay? So this first one, all right, that is just a definite integral. So I just want to give some names to this and some thoughts about these different types of integrals. Okay, this one has a 3 and a 4 in it. This is just a fixed piece of area. This is, we can find this by doing 1/3 x cubed from 3 to 4. We could plug a 4 in there. What's 4 cubed? 64. That'd be 64 thirds minus 3 cubed is 27. That'd be 27 thirds. 64 minus 27 is what? 37? Do that right? which would be 12 1/3. I think I did that right. So that's just a fixed piece of area. It's a numeric answer. That's called a definite interval. Okay? Now, what was this? If we know the left edge, but we use an X here for the right edge, which then means, of course, we got to use something else down here. What did we call this? That's an area function. This is an actual function. This is not a number, but it's a lot of numbers. It's for different right edges, for different X's, it's got different areas. So it's a whole bunch of ordered pairs. X and then the area, right? Maybe, matter of fact, that would be worth writing down. It's X and then the area from 3 to X, right? And that it's a bunch of ordered pairs. It's a function, and we could graph it and so forth. It's a we also said the area function is what? It's the antiderivative. Matter of fact, when we were doing the quiz, we had a problem somewhat like this where we could find the formula of this. It's a function. We could actually do this. Remember, it was 1/3 t cubed. One way we did it, and then we went from 3 to x. Remember when we did that? So now we can plug that in. That's going to be 1/3. We plug an x in. That's 1/3 x cubed minus 1/3 times 3 cubed. And what's 1/3 times 3 cubed? 9. So wouldn't this be 1/3 x cubed minus 9? Isn't that what that would be? See the difference between the first one and the second one? The first one is just a definite integral. It's a fixed piece of area. The second one is this thing called the area function. It's the antiderivative. But we plug in an x, plug in 3. It's an actual function. It's the function 1/3 x cubed minus 9. It's a specific antiderivative. That's what the area function is. It's a specific antiderivative because we know the c value, the plus c, right? It's an antiderivative, but it's a specific one, a unique one, because it's got a unique left endpoint, 3. Okay, now what do you notice on the last one? What is that? Well, that's all possible area functions, right? Because what's different about this one from number 2? We don't know the left endpoint, right? So the left endpoint would be all those. So by changing the left endpoint, we get all those vertical shifts, right? We get all those vertical shifts. So it's all possible area functions. So it would be, here it would be 1/3 x cubed plus c, right? There would be no way of finding the c value. It would be a general antiderivative. Make sense? So the last two are both area functions. It's just that number 2 is with a specific left edge, so it's a specific antiderivative with a specific c value that we can find. And the bottom one is just all the possible area functions with the plus c tacked on. So that last one is where we're at right now. And so I heard somebody say indefinite integral. This one we call, so this one up here we call a definite integral. This one down here we call an indefinite integral. And so the idea here is, well, if we don't know the left edge, and the right edge is variable also, the right edge moves, and the left edge could be somewhere else, why even put them on there, right? On that last one, why even put a and x, right? I mean, why even put them on there? So what we do with an indefinite integral is we write them like this. So what we do is we just leave them off. Just leave them off. Because we don't know them anyway when we're doing an indefinite integral, right? So these are indefinite integrals. So what those are saying is just find the antiderivative and tack on a plus c. What we're doing is this bottom one right down here when we do an indefinite integral. Just find the area function, just find the antiderivative, tack on a plus c. That's all you're saying. Okay? All right. So when you see a problem like this, the integral symbol with no numbers on it, that's what they're telling you to do. Okay? So, page 333 in your book. All right, here I've got a picture of it right here. Page 333 in your book has 9 antiderivative rules. That's it. That's what you got to know for antiderivatives. So you need to understand that doing an antiderivative is a different scenario than doing a derivative. When we learned about derivatives, we had this whole page of derivative rules. Right? You had to know all these. Now the nice thing about it is if your function looked like this, then you do this. Right? I mean, that's what we did. And we memorized all those, and then we ran into a lot of algebra we had to do, and we had to do some simplifying and stuff like that. You just followed the rules. But now understand what we're doing with the antiderivative. We're just going backwards. So if you've got a function that's 1 over u, the antiderivative is ln u. If you've got a function that's 1 over 1 plus u squared, the antiderivative is arctangent. 1 over 1 square root of 1 minus u, the antiderivative is arcsine, and so forth. Now you see these u primes and all that stuff in there, and that's the stuff we have to deal with. So if you look at the right side of this, that does not include all the different types of functions there. If you look down the left side, yeah, we pretty much exhausted all the different types of functions we could have. I mean, we went through all of them. And we got rules for all of them. But now we're going the other way. Well, the right side is not an exhaustive list of different functions, right? I mean, the book says doing antiderivatives is more of an art than a science. Derivatives is more of a science. Here's the rules. Follow these rules. Here you go. Antiderivatives are more about being creative, more about recognizing if it looks if it's got this kind of a pattern to it, then maybe I approach it this way and so forth. Okay, so you've got to think of it that way going in. But here are the ones you do have to know. You need to know that if you got x raised to a power, you're going to do the power rule. Now, somebody brought it up this morning. We had a nice bunch in here this morning. They got a nice extra little bit of help this morning on doing these. But if you raise this up 1 and divide, you have to do that. But notice it says not if you have a negative 1 power. If you've got x to the negative 1, you cannot do a power rule. Because what would you do? You'd raise that up to a 0 and divide by 0. You can't divide by 0. Well, that's taken care of in this one. If you have x to the negative 1, that's this. What's the antiderivative 1 over x? ln of x. Now, I think there were some people on the quiz that ran into some trouble. If you have 1 over x squared, is the antiderivative of that going to be a natural log? That's not natural log. That's a power rule. You write that x to the negative 2. The only time you've got natural log is when it's 1 over x to the first, right? Natural log is not used when it's squared or cubed or something like that. Okay, that's power rule. All right, so the antiderivative 1 over x. Now let's talk about these bars. Why are there bars here? Well, you can't put a negative into natural log, right? Can't do natural log of a negative, right? We've talked about that from the beginning here. You can only put positives into natural log. Now, we didn't have that problem in a derivative rule problem because the problem doesn't exist. If I give you this function, ln x, I've given you the log function. It's already assumed that x has to be positive there, right? It's a natural domain. X can't be positive in the log function. So when we do the derivative, we get 1 over x. We don't have to put bars around that. X is going to be positive. And plus, in 1 over x, it'd be okay if x was negative anyway, right? Not a problem. But when we go the other way, it's different. When we're given this as our problem, could x be negative right here? Could x be positive? The only thing x can't be is what? X can't be 0. But x could be negative. Well, when I do the antiderivative, if I only write this, I got a problem. Because since x in my original problem, x could be negative. When I do the antiderivative, I don't want x to be negative here. I can't put a negative into natural log. So what I do is I put bars on it, and then that'll fix that. So if x is negative, the bars will turn it to positive, and then we'll be okay. So that's why when you do an antiderivative of 1 over x, you have to put bars around it in your answer. And it'll be wrong if you don't have it. Okay? All right. So that's why those bars are there. It's a domain issue. All right, antiderivative e to the x is just e to the x. Now, this is one that you probably have to study a little bit. This is 2 to the x, or 3 to the x. And remember when we did a derivative, we have to kick out an ln2 or an ln3, while you're doing the antiderivative, would be the reverse of that. You have to kick out a 1 over ln2 or 1 over ln3. Okay? That's not going to show up very often, so we don't really have to worry about it too much. Antiderivative sine is negative cosine, antiderivative cosine is that. Secant squared, antiderivative is tangent. We're not going to do the cosecant ones. Those won't show up. They were in our derivative rules, but we won't worry about them. So antiderivative secant squared is tangent, because the derivative of tangent secant squared. And then here's the arc sine. Now, in your book, it's got the dx up top. I told you about that. I usually like to write a 1 there, put the dx up on the side. So if you see a square root 1 minus x squared on the bottom, think arc sine. You see a 1 plus x squared on the bottom like this, think arc tangent. That's it. That's it. If you know those basic antiderivative rules, right, then our job from here on out is how do we turn the functions we're given that we're supposed to do antiderivative, how do we turn them into something like this so we can do it, okay? Well, that's where things like U substitution come in. All right, so here we go. Let's go through a few. You don't have to write them down if you don't want to here, but just a few. What's the antiderivative of x squared? 1/3 x cubed plus c. Boom, done. Sorry, there probably won't be any that easy on the game. Okay. Antiderivative sine? Negative cosine. Now, if you're ever unsure when you do an antiderivative, remember we said more art than science. The nice thing about antiderivatives is you can always check them by doing what? The derivative. You can do the derivative, which we have a set of rules to do. Derivative of cosine is negative sine, but then the negative would cancel the negative, be positive. Oh, it worked. Bring the 3 down in front, cancel the 1/3, you get x squared. C would disappear. Okay, it worked. Okay, so then we get one like this. Now, this could be on the gateway test. I would say if you have some easy, some medium, some hard, to me, this is an easy. Okay? Now, it might not be today, but 5 days from now, could be. Okay? All right, so here we go. Do the antiderivative of this. So what's the antiderivative of 3x to the 4th? Raise that up to a 5. Divide by 5, so 3/5 x to the 5th. Minus. What's the antiderivative of e to the 3x? Okay, now there's a 1/3 there, right? Now if you're unsure about that 1/3, let's do this. Let's pretend that you just think, oh, e is its own antiderivative, so it's just e to the 3x. Remember we said we could check it? So let's check it. What's the derivative of e to the 3x? E to the 3x times 3. Oh, wait a minute. Is there a 3 there? No. There must have been something out in front of this, because remember, constants just hang out there anyway. There must have been something that canceled out that 3. What would cancel the 3? A 1/3. Now, sometimes people get to thinking, oh, so you mean whatever the inside is, I just do the derivative and divide by it or do the reciprocal. That's not true. Not if there's x's. That only works if there's just a number in there. If there's just a number in there, like a 3 or a 2 or something like that, then yeah, you can kick out a 1/2, kick out a 1/3. And I think that's the best way to do it. If you understand that, that'll save you a lot of trouble. You won't have to go through like a U substitution or something, which I'll show you here in a minute. So understand, do the antiderivative, you're going to kick out a 1/3. All right, plus, what's the antiderivative of that? Natural log bars x plus 3. Because all that is a left shift of a 1 over x graph, is all that is. Now, if that was x squared, that's a different story. If that's an x squared, then it's not an LA problem. Only if it's x to the 1st power. But if you just have an x plus 3 or some kind of shift of an x, then it's still natural log. Again, test it. What's the derivative of this? It'd be 1 over x plus 3. Now, when you do the derivative of the bars, you have to worry about those bars. Those are just there to make sure x plus 3 is positive. So when we do the derivative, you don't have to worry about it. Okay, so it's 1 over x plus 3 times the derivative inside, which is 1. And sure enough, the derivative of that would be 1 over x plus 3, so it fits. Minus, what's the antiderivative of that? Arctangent of x. So these are all, and then plus c. These are all ones right off of, with a little bit of adjustment on a couple of them there, right off of page 333. So those are basic antiderivatives we need to be able to do. Okay? All right, so you might have one like that or two of the gateway tests that are like that. Just kind of basic ones with a little bit of adjustment with the 1/3 we had to pick out. So, okay? All right, so then you get one like this. What happens when you get stuff on the inside? So this is what led us into this u substitution thing. So let's go back to derivatives. What's the derivative of sine x cubed? Cosine x cubed times 3x squared, derivative of the inside. Now we might write that 3x squared cosine x cubed, maybe it doesn't matter, that's just rearranging, I don't care about that. That is the derivative of that. So therefore, it makes sense that if I had this problem and asked for the antiderivative, it would be what? Wouldn't it have to be that? Plus some c, right? There could have been some constant on there, because whenever we do the antiderivative, we don't know. There might have been a constant, because when we do the derivative, that constant would go away. So we don't know. There might have been a constant there. So that's easy, right? When you see it written like that. Okay? Now, let me make a comment here. Derivatives, typically the function itself that you started with on the gateway test when we did derivatives was pretty simple, usually. But then the derivative was often messy. You remember that? A lot of times you start with a fairly simple function, and then your derivative, like quotient rule. Remember some of those quotient rule ones? Messy. So, derivative, function, simple, or the original function simple, and then the derivative was messy. So what do you suppose would happen? What would be the case when you go backwards? Might start out messy, but the answer would be fairly simple, right? Kind of like this situation. Look at what we started with. Kind of messy to start, but pretty simple when we finish. Well, it makes sense that it would be that way, because a lot of the derivatives were the reverse of that, right? So it's not unusual for your integral to look like a big messy thing, and you think, oh my God, this is awful. No, that's a lot of times that's good that it's messy. Remember the one I told you had no antiderivative? Look how simple that thing looks. It doesn't have an antiderivative. Okay? So it's good that they're kind of messy. So now, so we just saw that the antiderivative of that is that because of the work we did up here. But now let's, so this leads into this idea of u substitution. I showed you one like this earlier, but let's do this one. So now let's pretend we were doing this from scratch. So we were faced with this problem right here, right? And we're like, oh my God, what's the antiderivative of that? Doesn't look anything like page 333. So we've got this thing called u substitution. So what we do with u substitution, so instead of going through a bunch of what the homework problems was and working those for you, we're gonna go through some examples here together that you can go back and you can try to redo some of those. We'll look at a few of them, and then I'll add a few more onto it that you can keep practicing as we go along here today. Okay, so we have this thing called u substitution. What u substitution is, it says, all right, you're going to pick some u out of here. Now, there's going to be some strategies that you want to use. The very first strategy for what to pick for u is the inside. Now, there's going to be other strategies. Sometimes it's not the inside. Sometimes it's the bottom of a fraction. I had one on the board yesterday, number 5. It was actually the top of the fraction. How are you going to know? Well, then there's a second step that is the one that will tell you. Okay? So the first thing you look for is, I'm going to let u be the inside. Do I have a logical candidate here? What would it be? X cubed. So I'm going to let u equal x cubed. Now, what was the second step in u substitution? Do the derivative of this. Now, I told you that the derivative of u would be u prime, but we're going to write it du over dx equals 3x squared. And then we're going to move the dx over. Now, I think right now, from this moment on, I'm going to quit doing that middle step. I'm going to quit writing this. Okay? I'm just going to quit writing. You can, I don't care. That's fine. But so I'm going to say to myself, I'm going to do the du. I'm going to do the derivative of u. So I'm going to think to myself, du, I'm going to think derivative of u. That's what that stands for, right? Technically, it's not quite the whole thing, but that makes sense. So, going to do the derivative, du, which would be 3x squared, and then there'll be a dx at the end. Okay? And where does it come from? It comes from just multiplying it over. I get tired of writing that every single time. So here we go. Now, here's the second reason. So here's what your thought process is of how do you pick something for you. Number one, you look for the inside. That's usually where you start. Could be other things too. But then the key to why you're going to want to pick that thing is you think the next step. You think, okay, what if I pick that for u, what's the du? So if I pick x cubed for the u, what's the du? 3x squared. Aha, it's setting right there. That's what I want. I want it to be setting right there, that derivative of the u. Now, if you go back to our derivative rules, you can kind of see that. Like in this problem right here. I'm working backwards. Well, what do I have in this problem? Or no, it's this one right here. In this problem, what do I have? I have a cosine, and then setting right next to the cosine is what? The derivative of the inside. So when I'm working this backwards, the best scenario I can have is if I have a function and then setting right next to it is the derivative of the inside. Because that's just going to give me that. Now, I wouldn't memorize that. I wouldn't think of it that way necessarily. But you can see why it's working that way. That's your thought process. You say, okay, if I let u equal x cubed, the du is 3x squared, which is sitting right there. That's going to be perfect. Because here's what your substitution looks like now. We're going to take that. I like to circle these to make sure I've accounted for everything. You'll see how in some problems that's important. So what is this equal to now? Cosine of u, right? X cubed is going to get replaced with the u. And then look at this part. I'll just underline it because they're not together. Look at that part, the 3x squared dx. What is that? 3x squared dx is the same as du. So I'll take those out and replace it with a du. Well, now look what I have. Now I have something that's on page 333. I have a nice, simple antiderivative I can do. What's the antiderivative of cosine? It is sine plus c, and then I'll take the u out, I'll put the x's back in, and that's how I would get it. Now, we know from the previous page, we know that was the answer from the work we had done, but you're not going to have that all the time, right? You're going to just start from here. So this is what u substitution is. Okay, now there are a lot of little bumps in the road and a lot of little twists and turns that this can take that we have to get used to, but that's a straightforward, simple as it gets u substitution. Because when you pick the u, the du setting right there, everything subs out real nice. Okay, let's talk about this one. Now, I would say you shouldn't need u substitution on this, right? What is the answer to this one going to be? Sine of, inside always stays the same, right? Isn't there going to be a 1/5 out there, though? Isn't this just like that e to the 3x we did a minute ago? We're going to have to kick out the 1/3. Now, I think it'd be in your best interest to just recognize that. That, oh, this is just a cosine. It's got a 5 in there. Okay, fine. Antiderivative cosine is sine. But I'm going to kick out a 1/5 because when I check this, when I do the derivative, I'm going to kick out a 5, and the 5 will cancel that 1/5. Right? But you could do a u substitution of it. It's got an inside. What would be the u?
5x.
5x. So I'm going to go through this. Write it down. Don't write it down. I don't care. But the u would be the inside. 5x. Now what's the du? What's the derivative of that? 5 and then a dx, right? Which would come from over the other side. Yeah, you say, but there's not a 5 there. That's true. Let's do our substitution. Cosine 5x, that would be just cosine u. And then what's dx equal to? Well, I got this 5 here. I can divide that over to the other side. Whenever I have a constant here, I can divide it over. That's fine. So dx is the same as 1/5 du. So I can take out the dx and replace it. Now I'm going to put my 1/5 out here because we talked about that. How constants, we can just pull them outside. That's a better place for it. And the du, we always want that at the end. So see what I did there? So now you can see where that 1/5 comes from. Right? When you do it this way, you can see, oh yeah, okay, it makes sense where that 1/5 came from. So the antiderivative of cosine is sine u plus c, and then I'm going to put my 5x back in, 1/5 sine 5x plus c. But it just saved you a lot of work if you could just see it on that one. Okay? But you're not always going to see it on ones that are more complex. All right. So, let's do one together here. Okay, let's do one that's more of a a tricky one here. Okay, so write this one down. Or be a good idea. Now, don't forget, sometimes you can do some simplifying, some algebra where you can simplify things. So always remember that. But this time we can't, because what we have here is we have x times 1 plus x squared to the 1/2, and you cannot distribute that, right, because of the 1/2 power, because of that power. So you just can't do anything. So what would be a logical candidate for the u? Because it's on the inside. To me, a logical candidate for the u is the 1 plus x squared. Now, not only that, but I'm thinking a step ahead. What's the du going to be if I use 1 plus x squared? 2x dx. Do I have a 2x dx setting there? I have an x dx, and the 2 I don't really care about. I'll deal with it because I can divide it over. The constants I don't really care about, right? I mean, I care about them. They're going to matter when I work it out. But as far as is this going to be a good step? So that's why after a day or two of this, my hope is you would look at one like this, you go, oh yeah, let u be 1 plus x squared because the du will be 2x dx. I got an x dx setting right there. Perfect. Just what I want. Okay? So, du, the derivative, is going to be 2x dx, and now I'm ready to start subbing. So this will just be what? U to the 1/2 power. U to the 1/2 power. Right? Square root. I could put square root of u, but I know I'm going to do a power rule on it, so I'd rather have a power, not a root. What about the x dx? Divide the 2 over here. So x dx comes out in its place. 1/2 and a du. Now, is this one I can do? It's just a simple power rule now at this point, isn't it? Right? The 1/2 is just going to hang out there. I'm going to raise that up to a 3/2 and divide by 3/2. What is it when you divide by 3/2? Multiply by 2/3, right? Reciprocal. U to the 3/2 plus c. Now remember, the integral sign is gone. Once you do the antiderivative, the integral sign is gone. Okay? Just like if I tell you to do d dx of x cubed. You write 3x squared. You don't write the d dx again. That was there telling you to do the derivative. So once you've done the derivative, you just, that symbol is not there anymore. Well, same thing with this. Some people say, what happened to the du? Well, it's just like this problem. What happened to the dx? It was just there telling you to do the derivative with respect to x. This is just saying do the antiderivative with respect to u. So the du just goes away because it was just there telling you to do it with respect to u. Okay? So we get this. Those 2's cancel. So this would be 1/3. Put our u back in, which is 1 plus x squared to the 3/2 plus c. You don't have to put it back as a root. You can just leave it as a power, and there it is. Okay? Again, we can always check these. You can always check them. I think it's nice to do sometimes, especially here in the beginning. Did we get it right? Well, what would we do? We'd bring the 3/2 down in front. What's 3/2 times 1/3? 3's cancel, that's 1/2. Inside left alone, 1 plus x squared. Drop that power by 1. 1/2 times the derivative of the inside. Derivative inside is 2x. 2 cancels the 1/2. Look what we got. X times the square root of 1 plus x squared. It worked. Okay? This is the antiderivative. But could you have got that without going through this process? I don't think so. Right? Possibly, but good luck. Alright? Okay, let's look at this one. Now, This is far and away the most common technique for doing antiderivatives. Why? Because it's a reverse of the chain rule. The chain rule is whenever you have something on the inside, you know, like multiply by the derivative inside. Well, think about it. With derivatives, that was the most common rule we had with derivatives. Most functions have something on the inside. So therefore, we use chain rule a lot. U substitution is kind of the reverse of that. So we use it a lot. Now, what do you notice different about this one? It's got an A and a B, the 1 to E. So this is actually going to be a number answer. So what we're talking about here is a fixed piece of area from 1 to E, and this function is whatever that crazy function is. So we're talking about a piece of area here that we're finding from 1 to E. Okay? This kind of relates to number 11 and number 13 on today's homework. Okay, you're going to see how we're going to do that here in a minute. All right, so, but we start out the same way. Remember, it's big F of B minus big F of A is what we're wanting to do. Well, the first part of that is finding the antiderivative. We don't need the plus C, so we don't have to worry about that, but we need the antiderivative. So everything we do is still the same. So we're going to pick a U. What do you think would be a good U? ln x, because it's on the inside. But also, what's the du? Derivative of ln x is 1 over x dx. Is there a 1 over x dx setting there? There absolutely is. That x on the bottom is really a 1 over x dx. Matter of fact, if you don't believe it, you could rewrite this. I usually don't. But you could rewrite this as ln x cubed times 1 over x dx. That's actually what this problem is. So there is a 1 over x dx setting right there. So this is going to be a really good one for us, for U substitution. So we're going to U be ln x. The du is 1 over x dx. Now I usually just, when I sub these, I usually do it this way. So I've got this. I've got, what would that be? U to the third. So that's U to the third. And then I usually just circle it like this. But understand that that is not an x dx. That's a 1 over x dx. Okay? That's important. So sure enough, 1 over x dx is just du, and look how nice that is. Now, I got an issue. What did I not circle in blue? The 1 and the e. I did not. I've got to sub those out also. Now, technically I don't, but we're going to, okay, to get used to it. But at the end of the day, I could go back to x's, but why do that extra step? So, in other words, you got to understand, what are these values? Well, they are x values. See, here's the 1 and the e right here. They're on the x-axis, right? They're x values. I'm taking out the x's and putting u's in here. So this number and this number need to be u's, not x's. Well, how can I change x's into u's? With that equation right there. So these are x's. So I'm going to take this 1 and I'm going to plug it right there for that x. What's ln of 1? 0. So I just sub that out. I'm going to take this e and plug it in for this x. What's ln e? 1. So when x is e, the u would be 1. So that's going to be 1. So I've now converted it into that. Now notice, that's a whole different function. If I was going to graph this u cubed, that's a whole different function than this function. And instead of from 1 to e, it's 0 to 1. But guess what? What we're saying is they have the same area. The area under this from 1 to e is the same area as under this function from 0 to 1. So now all that's left is for me to do the antiderivative, which would be 1/4 u to the 4th. Put my right bracket, 0 and 1. Plug the 1 in there, I get 1/4. Plug the 0 in there, I get 0. And I get my answer 1/4. Remember, this is a definite integral, so we should get a number answer. Now, what I was saying is, technically, I don't have to change those numbers. I could have done this 1/4 u to the 4th and then put my x's back in. So when I did this here, I could have just left this blank, I suppose. I don't think it's a good idea, but I could have left this blank, done my 1/4 u to the 4th, then put my ln x back in like I have been, right? Then went from 1 to e. You see what I'm saying? So now you plug, but look what ends up happening. You end up doing the same thing. So now I plug the e in here, ln e is 1, 1 to the 4th is 1, that'd be 1/4. I now plug my 1 in, ln of 1 is 0, 0, that's just 0. And then I get 1/4 that way too. Right? So I could have, on a definite integral, done my u's, went back to my x's, and then used the 1 and the e. Or I could just change the 1 and the e into u values, and then do it that way. To get the same u. Okay? Alright, and that's what 11 was talking about. They did the u substitution on 11 and 13. They did the u substitution for you. You just had to change those values. So I can help you with that. I helped a bunch of people this morning with that one. Okay, let's do 2 more real quick here. Now we'll give you some more time. Yeah, 2 more. All right, let's do this one. What do you suppose you're going to pick for u on this one? Square root of x, x to the 1/2, because it's on the inside. Now again, I think you always ought to be thinking a step ahead. If I do this, if I let u equal x to the 1/2, what's the du? 1/2 x to the negative 1/2. Negative 1/2 means that'd be an x to the 1/2 on the bottom. Is that what I got? That's what I got. Again, so you'd say, good thing. That's what I need. Okay? So the du is 1/2 x to the negative 1/2 dx. So the top of this ends up being just sine of u. Oops. So that takes care of that. And then what about this 1/2's in the way? There's no 1/2 up here. Multiply it over, that'd be 2 du. And then this would be 1 over square root of x. I'm just rewriting that so I can tell. So that x to the negative 1/2 is 1 over square root of x dx, which of course is exactly what I got right there. So that will get replaced with a 2 and a du. See how nicely that worked? And I end up with an integral that looks like page 333, a nice easy one to do. What's the antiderivative sign? Negative cosine. And the 2 will be on there as well. Plus c. And then I'll put my square root of x back in, or x to the 1/2, either one, I don't care. That. That. Again, messy looking function to start with, fairly simple looking one at the end. Not unusual that it would happen that way. Okay? All right, we're going to do one more problem. Now this is very much like number 10. This is very much like number 10 on your homework was, where, now this one you're actually going to let, now they told you what to let u equal on number 10. Number 10, help me out here, and I talked with a lot of you this morning, so I don't want to go through it again, but you got x, wasn't it x over x plus 1?
Yeah.
Okay, now the problem with a fraction like that, number 1, there's no inside what to pick. Now they let u equal x plus 1, right? So on that one, if we let u equal x plus 1, what's the du? Just 1 and then dx, right? So we would just write dx, right? So when you do that, so now when you sub that, this was number 10 in the homework. So when you sub that, the bottom is going to be u. And then what's the top? Well, you've got this, because here's the problem. There's no x in here. That now there's this dx, right? Would just get replaced with du, because they're equal. So you got this like extra x thing.
Is it u minus 1?
Yes. You can take this equation and you can subtract 1 from it. X would equal u minus 1. So over here on top, you would have u minus 1. Now, so the question was this morning, well, that looks a lot like what you started with. The only difference is kind of like the top, bottom, or flip. Well, there's a huge advantage to that. Because what can we do when we have a single denominator? We can split it. See, look at it this way. If you have 3 plus 4 over 7, a single denominator, you can split that into 3 sevenths plus 4 sevenths. That works beautifully. But if you have the reverse of that, if you have 7 over 3 plus 4, you can't split that. That's not 7 thirds plus 7 fourths. You can't do it. You can't split a denominator. But you can, if you have a single denominator, then you can split it apart. So now what we can do is we can split that. U over u, which is 1, minus 1 over u, right? And then you can do the antiderivative from there. So that's the key to number 10. All right? Yes, ma'am.
Why doesn't it have to be x plus 1 to the
Because if you want to move this up top, are you talking about what u is or what I put it in here?
Yeah, over here.
I only want it to be just the x plus 1. You're right, because if I let u equal x plus 1 to the negative 1, then that makes it a lot more complicated. The key is I let u equal x plus 1, so when I sub it out, it's on the bottom. I just put the u on the bottom. Now I got u to the negative 1, basically. So it is the same. But yeah, if I let u equal x plus 1, negative 1, it just makes it more complicated than it needs to be, and it wouldn't work. It wouldn't work. Okay, because then I wouldn't be able to solve for this x here. Okay? All right, a lot like this one. Remember, let me see. I'll let u be that up there. Yeah, I guess we didn't really have one like that. Yeah. So, good question, though. No, I just let u be the bottom, and so then that just puts a u down there. But again, so that's why the strategy of letting u be the bottom is sometimes a good thing, because if the bottom has several terms in it, if you let u be that, now you've turned it into a single denominator. And single denominators are good, because you can split apart the fraction. Okay? All right, let's look at this one. It's kind of a similar situation. I'm going to let u equal what? 9 minus x squared, right? Because it's the inside. Okay, it's the inside. Now, when you do that, and this is, we're jumping into a pretty tricky one here now, right? So we kind of got the basics a little bit. I think we feel better about it, right? Raise your hand if you feel a little better. All right. So we kind of got the basics. Now we just got to practice that. But now what would be some troublesome things that would come in? All right, now, so let's say we pick u to be that. What I tell you, think of the next step. What's the du? Negative 2x dx. Now, do I have an x dx setting there? No, I have an x cubed dx. Well, having extra x's is okay. Remember up there, I had an extra x I was able to deal with. Having extra x is okay. So I'm going to go ahead and keep going with this. So I got du is negative 2x dx. Now the negative 2 is in the way, so I'm going to move that over, negative 1/2. Divide that over. And I got this x dx. Now, you said, okay, you don't have an x dx, you got an x cubed dx. But see, I would disagree. I think there's an x dx there. Because x cubed is what? Isn't it x times x times x and then dx, right? So can I take one of those x's and stick it with the dx? Answer is yes, I can. Because it's multiplication, right? It's all multiplication. Think of the dx as multiplied on there, and you can do that. So I can take the x cubed and do that, and I can peel that piece off. Okay? So now, let's look at it. So let's look at my substitution. So this is going to be what? U to the 1/2. Okay? And now, I'm going to take my x cubed and I'm going to make that x squared times x. So I can peel this x dx here. And what can I replace that with? X dx is, no, it's negative 1/2 du, right? So x dx is negative 1/2. Now I'm going to leave myself a little space here because I happen to know what's coming. Okay? Because I know I've still got some stuff left, so I'm going to leave myself a little space. So I got my negative 1/2 of my du. All right. I still have an x squared left. Can I get an x squared from this right here? I can add the x squared over to this side and subtract the u. So x squared is what? 9 minus u, isn't it? So I can take that x squared and I can replace that with a 9 minus u. Now let's look at this a minute. It's kind of like, gosh, that doesn't look a whole lot better than what I had. But it's actually a lot better. Because here's the problem. In the original, and I talked about this at the beginning of the period, can we distribute this x cubed through here? We can't because we got this quantity that's a power. But look what I've traded it for. I've traded it for u, a single thing, to a power, and then this. Can I distribute this? Now I can distribute because this doesn't have a power on it. So this looks a lot like what I ended up with here, but what I ended up with is actually a lot better because I can now do some algebra. Okay? So now I can take this and I can distribute, and I get 9u to the 1/2 minus u to the 3/2 du, because you add those powers, right? And I'm going to leave the rest, you guys know, because we need that work time. So you're going to finish that, fine. You want to go back into the homework job. But now it's just a matter of raising. Now there's going to be some fractions, and you're going to have to be careful getting the fractions right. Then negative 1/2 has to distribute to both of those, but you're going to raise this up to 3/2 and then divide by 3/2, which would be 2/3. So you have 2/3 times 9. You have to get that fraction right. Here you're going to raise that up to 5/2. Divide by 5/2, which would be 2/5. You got to get that fraction right. Then you got the negative 1/2 to distribute and all that, so it's going to get messy with that. But basically we should be able to handle it that. Okay, so we've seen some weird kind of scenarios that come up, but we got the basics down, I think, and we just need to practice it now for another day. So tomorrow we'll go into, probably stay with this mostly tomorrow. There are some other techniques we got to learn. One, basically, other technique we got to talk about yet, and then have some more practice. A lot of practice, right? Some of you did not do enough, I don't think, before the last gateway test. You might have realized that once you got into it. Because remember, once we take that anti-derivative gateway, we move on to new stuff, and you've got to pass it. So it's best to pass it the first time or very shortly after. So between now and next Tuesday or Wednesday, study. I mean, practice. Use up a lot of paper. All right. So here's what we're going to do. 5.4. You already have those other problems, 1 through 9 odd, and those other ones I gave you. Maybe still have something to do there. You better do at least, I would say, 10 more. Okay. I think on the assignment sheet I wrote, what did I write on that assignment sheet? In the bold there, it says do sum of 23 through 73. So on that page 3, it's page 341, I believe. So 23 through 73, you better try to pick out at least 10 more of those. Plus, I would say go back and revisit some of the ones that were on today's homework you struggled with, or didn't get a try or whatever. So the reason I said 10 there is because I assume you probably have at least 5 or so you probably still need to do from today's homework. I think that's a fair number of problems to try for tomorrow. That's a minimum if you want to really pass this the first go. Okay? So here we go. Here's the answer book up here if you want to look.